Okay, welcome back to video number 9A. Okay, so here's the schematic, and basically it's a pretty simple classic linear design. And I actually got the schematic on repeaterbuilder.com under Astron, one of the manufacturers, and they have a lot of information, a lot of different Astron type supplies. And you notice down here they give you some pin voltages at load and no load. So I'm going to go over how this whole thing works. So basically when you're troubleshooting this, you want to start right here at the AC. You want to make sure that your fuse is okay. On mine, I actually had to replace the fuse hole that was broken off. So this thing was in pretty rough shape when I got it. Then you have your switch. You want to double check your switch. There's also on some models there's a neon bulb inside that switch that usually goes out, or the switch gets fused together, which is a common thing. Right here you have a MOV, a metal oxide varistor, and this is to help for any surge coming in from the AC. So this guy, I believe, is 150 volt MOV, so if the voltage gets above 150 volts, this guy starts to conduct and blows the fuse. It's a protection device. These can go bad. I've seen them go bad in other pieces of equipment, and usually you'll see a big crack in it, or it'll be charred, or you'll definitely see physical damage on that part. I've actually seen them vaporized in some applications. We also have our transformer. So if you got a good transformer in here, chances are you can resurrect this thing pretty easily. The transformer is the big key in here. To replace that's pretty expensive. Right here we have our rectifier diodes. This is set up as a they're actually using a bridge rectifier in here, but they're only using half the side. Let me pan over to the bridge rectifier here. Right on the back, they're not using the whole thing. They bring in the AC, and they have the DC coming out here. So they have your AC in, and they have just plus coming out, because they have some center taps in here and stuff, which we're going to take a look at in a minute. So back to the schematic. I got a new tripod here, so kind of bear with me. Whoop. Okay, so we have our rectification going on here. Right here, there's two big caps. This is the big guy, the blue one down here. It's 32,000 microfarad. Then you have another 1,000 microfarad, and you have this guy here. This is another protection diode, just in case something catastrophic happens to the bridge rectifier. This guy protects the circuit. A lot of protection in this thing. And they actually have a set of two windings. One winding does the 12 volt high power aspect, and another winding does the low power to power up this circuit right here. This is your precision voltage regulator. This is the LM723. They have a UA723, which is made by Fairchild. So this whole supply was actually designed in the 70s. They're still being produced today, so that could attest for the design quality of this. And this is a classic regulator design. You can actually see this on the data sheet of the 723. It's almost identical to what's on the data sheet. Right here is your driver transistor to power up these pass transistors, and these guys do the majority of the work right here, so that they're on heat sinks, and it's a 2N3771. I believe it crosses over to a NTE 181. You can double check on that. or you can actually use a higher spec IC collector current. I've done that on a couple supplies too. I've actually doubled it. Right here, these series resistors. On some models, they'll actually throw a meter across these so it can actually measure out current. But that's for current limitation on that guy. And right here, this is an interesting circuit. This is the crowbar circuit. So if the voltage gets above a certain point, this guy will conduct and turn on and short your output directly to ground and hopefully blow that fuse in the beginning. This is the problem I had on this supply too. This was completely shorted out. Usually when SCRs fail, they fail as a short. And that's what's the case in this guy. So every time you turn on the supply, it would blow a fuse. And that was because this guy was shorted out. So that was another problem I had. Once I replaced these pass transistors, that basically what happened, something happened to the output. Either went too high, or these guys probably overheated and the voltage went too high, which kicked on the SCR. The SCR shorted out and blew out the fuse, and the person came, kept replacing the fuse, it kept blowing out, and then eventually that SCR failed and shorted. And that's how I got the supply. All that stuff was what was broken on it. I had to replace that stuff. And finally, we have another filter cap out here. So, very classic design. It gives you all the voltage measurements with load and without load, which is very helpful. So, that is my review on the Astron RS-20. Big thumbs up. I mean, it survived a 6-foot drop with very minimal damage. This sheet metal, really. No electronic damage at all. If you want to have like a battery backup system on this too, what I use is a small lead acid battery. I use a 18 amp hour lead acid battery, and I put the lead acid battery in parallel with the supply, and as long as you keep the voltage down below the quick charge rate, I believe it's around 14 volts or so, as long as you keep it down below like 14.1 volts, you can do what's called a float charge. And you can, on this battery, if you look up the data sheet, this is a big MK 18 amp hour battery. I put this in parallel for emergency power, so in case the power goes out, that guy kicks in, and it's all wired in parallel, so it's always on. So it's always charging, and if I lose power, it's not a problem. And plus it gives a little bit extra current boost. If I have a high current load like my HF radio, if I plug in a lamp and I have the HF radio going, when I transmit at 100 watts, it'll pull the supply down if I just have the supply alone. But if I have that battery in there, it gives it a little extra oomph for current. And it helps in filtration too, any type of AC coming through. It's like a giant capacitor in a ways. So you can always do that, and that's typically of most lead acid batteries. You can put it in that float charge rate, and you should be able to keep it on there indefinitely, as long as you don't exceed that charge rate, that charge voltage, the quick charge. And but just take a look at your data sheet for your battery, and it'll tell you what the float voltage is for that. And that's it. That's my review of this guy. I'll be fixing this up this week. Rebending out the sheet metal, getting it back to spec, and hopefully I'll last another 20 years. Okay, see ya.